Tonight, we're going to explore one of the quietest contradictions in all of physics. It hides in plain sight. It is there in the sunlight resting on a windowsill, there in the faint warmth on the back of your hand when you step outside on a clear afternoon, there in the soft glow of every star you have ever looked up at and wondered about. It is there in the green of every leaf and the color of every sunset, in the glow of a candle and the light of a screen, and the slow fading gold of the last hour of a long summer day. It surrounds you constantly, from the moment you wake until the moment you close your eyes, and almost no one ever stops to question it. Light has no mass, not a small amount of mass, not some sliver too faint for our finest instruments to catch, but none at all. A single particle of light, a photon, weighs nothing. You could gather every photon that pours out of the sun in one single second, an unimaginable flood of them, more than there are grains of sand on every beach on Earth, and on any scale ever built, they would still register as exactly zero. And yet that same weightless light does something remarkable. It carries energy, real, measurable, world-shaping energy. The warmth you feel on your skin on a clear afternoon is energy that left the surface of the sun a little over 8 minutes earlier and crossed roughly 93 million miles of empty space to reach you, traveling the whole way at the fastest speed anything in the universe is allowed to go. The green of every leaf is light being caught and turned into the sugars that feed a plant, and the creatures that eat the plant, and the creatures that eat them, so that very nearly the entire living world, the whole vast web of it, runs on energy that arrived here as nothing more than light, massless light, doing the heavy lifting for an entire planet. Even the seeing itself is light at work. The image of these words reaching you right now is light, bouncing off the screen and falling into your eye and being turned, somehow, into sight. We are creatures who live almost entirely on the energy and the information that weightless light brings us, and we so rarely pause to ask the obvious question. So where does that energy come from? It is a fair question, and a strange one, because almost everywhere else in physics, energy seems to want a body to live in. We learn early that a moving thing carries energy because it has mass and motion together. A rolling boulder, a thrown ball, a comet falling toward the sun. Take away the mass, and the usual rules say the energy should vanish with it. Light refuses to follow that script. It has no mass to speak of. And still it warms worlds. Still it feeds forests. Still it pushes on the things it touches, gently but truly, the way a faint breath of wind leans against a sail. Spacecraft have actually flown on that push alone, with no fuel of any kind, carried forward across millions of miles by nothing but sunlight pressing against a thin silver sheet. We will sit with that mission later, slowly, when the time is right. For now, simply hold the shape of the puzzle in your mind. Something with no weight at all is one of the most important carriers of energy in the entire universe. That should feel impossible. The fact that it is not impossible, that nature solved this long before anything alive ever thought to ask about it, is the whole reason we are here tonight. And here is where you can let your shoulders drop, because we are not going to chase this answer. We are not going to rush it, or stack it into a frantic countdown, or hurry you towards some loud conclusion. That is not what this place is for. Tonight, we are going to wander toward the answer the way you might wander a long beach at dusk, in no particular hurry, letting one quiet idea hand you gently to the next. We will meet a handful of people who slowly piece this together over a century and a half, a bookbinder's apprentice and a few reluctant geniuses, and we will follow a single beam of light from the heart of the sun all the way to the edge of time. There is nothing here you need to memorize, nothing you need to keep up with. If you drift off somewhere in the middle, that is perfectly fine. The light will still be here. The sun will still be shining its weightless energy across all that empty space, and the words will simply carry on, waiting for you whenever you happen to come back. So find whatever position lets you finally rest. Dim the screen if it is still bright. Let your breathing settle into something slow and unbothered, the way it does on its own when you stop asking anything of it. For the next couple of hours, you have nowhere to be and nothing to solve. There is only this one soft mystery, the one that has been resting on your skin your whole life without ever asking for your attention, and the long, calm path we are about to take through it together, out across the spectrum, into the atom, down into the core of a star, and all the way back to the first light of the universe. We will begin where almost everyone goes wrong, before we can understand what light truly is, and how something with no weight can carry so much. We have to gently set aside the picture most of us were quietly handed as children. The picture of light as a kind of tiny glowing substance, a little packet of stuff with fuel inside. It is a comforting image. It is also not quite true. And the moment we let it go, the real story, the stranger and far more beautiful one, can finally begin to take shape in the dark. The picture most of us carry, the one we were gently handed somewhere in childhood, goes something like this. Light is a tiny glowing thing, a little speck of bright material perhaps, with a small store of energy tucked inside it, like a battery or a drop of fuel. The sun makes these little specks, fills them up, and flings them out across space, and they slowly spend their brightness on the long journey until they reach us. It is a tidy story. It feels right. And it is one of the most useful wrong ideas in all of science, because the moment you understand why it is wrong, the truth finally has room to arrive. Light is not a substance. There is no glowing material at its core, no fuel tank riding along inside each ray. A photon is not a thing in the way a grain of sand or a droplet of water is a thing. If you went looking for the little bright object, hoping to hold it still and weigh it and pry it open to find the energy inside, you would come away with nothing. There is no there, not in the way we expect. And this is the first place the old picture quietly falls apart, because if light is not a tiny object carrying fuel, then the energy it delivers has to be coming from somewhere else entirely, somewhere stranger, somewhere we cannot see, but which is, even now, filling every cubic inch of the room around you. To find it, we have to go back to a quiet, self-taught man, working in a London laboratory in the 1830s. His name was Michael Faraday, and he had almost no formal education and very little mathematics. He had been born into poverty and started life as a bookbinder's apprentice, reading the volumes he was meant to be stitching together, teaching himself out of the very pages that passed through his hands. He came to science through sheer hunger for it, attending public lectures by the great chemist Humphrey Davy, writing them up so carefully that Davy eventually took him on as an assistant. From a bookbinder's bench he rose slowly to become one of the finest experimenters who has ever lived. But the mathematics that ran through the physics of his day, the dense, formal language of his more privileged colleagues, he never truly mastered. What he had instead was a kind of physical imagination, a way of seeing forces directly in his mind that almost no one around him shared. That gift showed itself most clearly in a simple demonstration you may have seen yourself as a child. When Faraday scattered iron filings on a sheet of paper and held a magnet beneath it, then tapped the paper gently, The little flecks of iron shivered and arranged themselves into soft, looping curves, arcing out from one end of the magnet and bending back into the other, ring inside ring. Most people who saw this saw a neat little parlor trick, a pretty pattern and nothing more. Faraday saw something he believed was really physically there. He became convinced that the space around the magnet was not empty at all, but threaded everywhere with invisible lines of force, a hidden structure filling the room, and that the iron filings were not creating the pattern, but merely revealing one that had been present all along, waiting in the apparently empty air. It was a radical thought, and a lonely one. The physics of the day preferred to imagine forces that reached instantly across empty distance, one object reaching out and tugging another, with absolutely nothing in between. Action at a distance, as it was called. Faraday was suggesting the opposite. He was suggesting that the space itself was doing the work, that around every magnet and every electric charge there stretched a real, invisible presence, what we now call a field, and that this field was where the action truly lived, carried from place to place rather than leaping instantly across the gap. He could feel the truth of it in his bones. He simply could not write it down in the formal language that would let other scientists take it seriously. That part would fall to someone else, someone who was, by a quiet coincidence, born in the very same year that Faraday first uncovered the effect we now call electromagnetic induction. His name was James Clerk Maxwell, and he arrived in 1831 in Edinburgh, and he had exactly the gift that Faraday lacked. Maxwell could see the pictures in his mind the way Faraday did, but he could also translate them into rigorous mathematics, and he spent years doing precisely that. Through the 1860s, he worked to give Faraday's invisible lines of force a mathematical body, to write down rules that captured how electric and magnetic fields actually behave. The result was a set of relationships among the fields that, in the compact form they were later given, comes down to just 4 statements. And though there is no need to carry any equations into the dark with you tonight, the 4 ideas behind them are worth hearing in plain words, because they are among the most quietly powerful sentences anyone has ever written about the world. The first says that electric charges create electric fields, that wherever there is a charge, the field reaches out around it. The second says that magnetism has no such isolated source, that you can never find a lone North Pole or a lone South Pole on its own, that the magnetic field always loops back around on itself. The third, which came straight from Faraday's own discovery, says that a changing magnetic field creates an electric field, and the fourth says that electric currents create magnetic fields, and here Maxwell added something subtle and crucial of his own. He saw, on grounds of pure mathematical consistency, that a changing electric field must also create a magnetic field, even with no current flowing through it at all. This small addition, almost an act of mathematical conscience, was the piece that made everything fit together. And when Maxwell put the third and fourth ideas side by side, something he had not been looking for came tumbling out of the mathematics. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. So imagine an electric field that is changing. It gives rise to a magnetic field. But that magnetic field, in being born, is itself changing. And so it gives rise to a new electric field, which is also changing, which gives rise to another magnetic field, and on, each one summoning the next into existence. Once that handoff begins, it can sustain itself forever, the electric feeding the magnetic and the magnetic feeding the electric, the pair of them rolling forward through space together, needing nothing else to carry them along, needing no medium, no material, nothing but each other. A self-renewing wave in the fabric of the field. That was what the mathematics described, with no one having put it there on purpose. And when Maxwell calculated how fast such a wave would have to travel, using only the measured strengths of electricity and magnetism, two numbers that had been gathered in laboratories with no thought of light at all, the answer came out at very nearly 300,000 kilometers every second. That was already a known number. It was the measured speed of light. Sit with how quietly enormous that is. Maxwell had not set out to explain light. He had set out to describe magnets and currents and sparks, the practical electricity of his age, and the equations answered a question he had never asked. They told him that light was not a separate, mysterious thing at all. Light was this self-sustaining ripple in the electromagnetic field, the very same field that Faraday had felt threading the space around his magnets. The glow of a candle, the warmth of the sun, the colors of a sunset, the entire visible world, all of it was electricity and magnetism, woven together and traveling. Maxwell drew the only conclusion the numbers would allow, that light is a disturbance moving through the same medium responsible for every electric and magnetic effect. Two great forces and the whole of the visible world, unified in a handful of lines that a patient person could write on a single page. There is something gently sorrowful in the timing of all this. Faraday died in 1867, and Maxwell himself died young, in 1879, at just 48 years old. Neither man lived to hold the proof in his hands, to see his invisible ocean confirmed by a deliberate experiment. The pictures and the mathematics agreed beautifully, but agreement on paper is not the same as catching the thing in the act. That final confirmation would come a few years after Maxwell's death, and it would come from a young German physicist named Heinrich Hertz, working patiently in his laboratory in the late 1880s. Hertz set out to test the prediction head-on. If Maxwell was right, then it should be possible to make these electromagnetic waves on purpose, to shake the field hard enough on one side of a room that a ripple would travel across the empty air and arrive on the other. So he built a transmitter, a device with a small gap across which electric sparks would leap, snapping back and forth very rapidly, jolting the field again and again at a tremendous rate. And on the far side of the room he set a receiver, nothing more than a simple loop of wire with a tiny gap of its own, a detector with nothing at all connecting the two but air and empty space. When the sparks jumped on one side, faint sparks answered in the loop on the other. Something had crossed the room. Something invisible had carried the disturbance from one place to another with nothing physical bridging the gap, exactly as Maxwell's equations had promised. And Hertz did not stop at simply seeing the answering spark. He set about proving, carefully, that whatever was crossing the room behaved in every way like light. He bounced his invisible waves off metal sheets and showed that they reflected. He let them overlap and found that they could add together or cancel out, the way overlapping ripples do, allowing him to measure their wavelength. He showed they could be bent and that they had a definite orientation in space, a property light shares. And when he worked out how fast they were traveling, the answer was the speed of light, just as predicted. He had made light, in a real sense, only at a wavelength far too long for any eye to ever see. He had made the first radio waves. The invisible ocean was real, and now anyone could send a ripple across it on purpose. The entire modern world of broadcast and signal and wireless connection, every radio and every distant transmission, traces back to those small answering sparks in a quiet German laboratory. And yet, in one of the most touching footnotes in all of science, Hertz himself saw no use for what he had done. When asked about the practical value of his discovery, He is said to have brushed it aside as nothing of consequence, a thing done only to prove that the great Maxwell was right. He died only a few years later, in 1894, still a young man, never knowing that the invisible waves he had pulled across his laboratory would one day wrap the whole of his planet in conversation. So let us put the new picture in place of the old one, slowly, because everything that follows rests on it. Imagine a vast, perfectly still lake at night. The water reaches out in every direction, further than you can possibly see, smooth and dark and silent. This lake is the electromagnetic field, and it is not somewhere far away. It is here, in this room, passing through the space between you and these words, filling the air, soaking through the gaps inside the atoms of your own hand. It is everywhere, all at once, and most of the time it simply rests, perfectly calm, asking for nothing. Now picture a single drop falling and touching that surface. From the point where it lands, a ring spreads outward, a ripple traveling across the stillness, carrying energy from the place where the drop fell to wherever the ripple eventually arrives. And here is the part to hold on to. The water itself does not travel across the lake. Each patch of the surface only rises and falls in place, lifting and settling as the disturbance passes through it. What moves, what actually crosses the distance, is not the water at all. It is the disturbance, the pattern, the shape of the motion, handed from one patch of water to the next, all the way across. That ripple is a photon. Not a little glowing object skating across the surface, but the disturbance of the surface itself. This is the heart of the whole matter, and it is worth letting it settle all the way down before we go on, because once it takes root, almost everything else tonight unlocks from it. When you feel the warmth of sunlight on your skin, nothing solid has actually arrived from the sun. No tiny bright pellets have crossed the void and landed on you. What has reached you is a ripple, a disturbance in the field that was set going 93 million miles away, a pattern of rising and falling in the invisible ocean that runs all the way from the surface of the sun to the back of your hand. The energy was never stored inside a little object, because there is no little object. The energy is in the ripple. It always was. And this is why the old fuel tank picture had to go. You cannot ask how much fuel is inside a wave any more than you can ask how much water a ripple is carrying from one shore to the other. The question simply does not fit the thing. The energy of light lives in the disturbance, in how sharply and how often the field rises and falls as the ripple passes by. And that single idea, once it takes hold of you, quietly reshapes everything we are going to wander through for the rest of the night. But it also leaves us with a softer, deeper question, one that the lake on its own cannot answer. A ripple on real water can be any size at all. You can disturb a pond by the gentlest possible amount, a touch so light it barely registers, or by a great deal, and everything in between, with no smallest possible ripple, no limit on how faint a disturbance you can make. For a long time, physicists assumed light worked exactly the same way, that its energy could come in any amount whatsoever, perfectly smoothly, dialed up or down like the surface of a real lake. It was an entirely reasonable assumption. The field seemed continuous after all, as continuous as water. It was also, it would turn out, not quite true. And the place where that comfortable assumption finally cracked, near the end of the 19th century, is where the calm surface of classical physics gave way to something far stranger underneath. That is where we are going next, slowly and in no hurry at all. For most of the 19th century, the lake held perfectly still in the minds of physicists. Light was a wave in the electromagnetic field. Maxwell had shown as much, and a wave could be any size you liked. The energy in a beam of light, everyone assumed, could be turned up or down as smoothly as a dimmer on a lamp, with no smallest possible amount, no step you could not make smaller. It was a comfortable assumption, and it worked beautifully for almost everything. The wave picture explained color and reflection, and the bending of light through a lens, and the splitting of white light into a rainbow. By the closing years of the century, many physicists felt that the great work was very nearly done, that the major laws of nature had been found and only the decimal places remained to be filled in. There was one ordinary, everyday thing, though, that the trusted physics could not explain, and the failure was not small. It was, when you followed the mathematics all the way down, absurd. The thing it could not explain was the glow of hot objects. You already know the effect, even if you have never named it. Heat a piece of iron in a fire and it begins to glow. First a dull red, then orange, then a brighter yellow as it grows hotter, edging toward a brilliant blue-white if you could push it far enough. Every warm object does this, even your own body, though it glows in infrared light your eyes cannot see. The color tells you the temperature, which is why a blacksmith can read the heat of the metal by its shade, and why astronomers can read the temperature of a star from its color. A cool star glowing red, a hotter one white, a hotter one still a faint blue. Physicists in the late 1800s wanted to describe this glow precisely. They wanted an equation that would tell them, for any temperature, exactly how much light should come out at each color. It seemed like a tidy, almost finished problem, one of the last loose threads before physics could be tied off and called complete. And when they worked it out, using the trusted laws of the day, treating the light as a smooth wave that could carry any amount of energy, the mathematics gave an answer that was deeply, gloriously wrong. To see why, picture the inside of a warm oven, a closed cavity with light bouncing around inside it, sharing its energy among all the possible waves it can hold. The classical reasoning said that the energy should be shared out evenly among all those possible waves. But the trouble is that there are far more ways to fit short waves into a cavity than long ones. As you look toward shorter and shorter wavelengths, the number of possible waves keeps climbing without limit. And if each one is to receive its even share of energy, then the total energy pouring out at short wavelengths should climb without limit too. A little in the red, more in the violet, more still in the ultraviolet, and then, as the wavelengths grew shorter and shorter, the predicted energy raced off toward infinity. Taken at face value, the classical laws insisted that every warm thing in the universe, including the embers in a fireplace and the skin on your hands, should be blasting out an infinite torrent of high-frequency light. The room you are resting in should be flooding you with a lethal storm of ultraviolet and beyond, simply because it is warmer than the deepest cold of space. Plainly, this does not happen. The fireplace glows softly and warms the room and harms no one. The mathematics and the world disagreed completely, and the disagreement lived right at the short wavelength, high-frequency end of the spectrum. Years later, it would be given a wonderfully dramatic name, the ultraviolet catastrophe, but in the moment it was simply a quiet nagging wrongness that no one could resolve. The best physics of the age, applied to the simplest possible thing, the glow of something warm, gave an answer that was infinite when it should have been gentle, and a wrongness like that, sitting in plain sight at the foundations, is exactly the kind of small crack that eventually brings a whole edifice down and lets a new one rise. Into this puzzle, in the year 1900, stepped a careful and rather conservative German physicist named Max Planck. Planck was not a revolutionary by temperament. He was 42 years old, deeply respectful of the established physics he had grown up inside, the last sort of man you would ever expect to crack the foundations of the field open. He simply wanted the equation to come out right. He wanted a formula that matched the real glow of real hot objects, the gentle curve that rises to a peak at some color and then falls away again toward the short wavelengths, instead of the curve that ran off uselessly to infinity. He had a good measurement of that real curve to match, gathered by careful experimenters, and he worked at the problem from every direction he could find. And after a great deal of effort, he discovered that he could only make the mathematics behave if he allowed himself one very strange assumption. He had to assume that the energy did not come out smoothly. Instead of letting the warm object release its light in any amount at all, in a perfectly continuous stream, Planck found that he had to imagine the energy could only be emitted in small, separate, indivisible packets, little bundles, with nothing in between them, and the size of each bundle, he discovered, depended on the frequency of the light. Higher frequency light could only be released in larger packets. Here was the quiet trick that solved everything. To make a single high-frequency packet, the warm object needed to gather a large amount of energy all in one place at one moment, and at any given temperature, large amounts of energy gathered into one spot are simply rare. So the very high frequencies, the ultraviolet and beyond, almost never got made at all, because the object could so seldom afford the price of even a single packet. The infinity vanished. The runaway was tamed. The curve bent back down toward zero at short wavelengths, exactly the way real glowing iron does, and it did so only because energy had been forced to come in steps instead of along a smooth slope. To make the numbers fit perfectly, Planck needed one new constant, a fixed number that set the size of these packets for a given frequency. It turned out to be an astonishingly tiny quantity, a decimal point followed by more than 30 zeros before the first meaningful digit, in the ordinary units of energy and time. That smallness is the whole reason the graininess of light had stayed hidden for so long. The steps are so unimaginably fine that, at the scale of everyday life, the staircase looks exactly like a smooth ramp, the way a beach looks like a continuous surface until you bend down and find it is made of separate grains. That tiny number is now called Planck's constant, written as a small letter h, and it would turn out to be one of the deepest numbers in all of nature, appearing again and again, wherever the world reveals its grainy quantum character. But here is the part that says something tender about how science actually moves. Planck did not believe his own discovery. Not really. He thought of the energy packets as a mathematical convenience, a bookkeeping trick he had been forced into to make the equation behave, not as a true statement about how the world is built. He spent years afterward trying to find a way around his own idea, to reconcile it with the smooth, continuous physics he had grown up trusting and loving. Long after, looking back, he described that original step as an act of desperation, something he had done only because he had exhausted every other path open to him. He had pried open a door into a completely new physics, and his very first instinct was to try and quietly close it again. There is a deep humility in that, and a deep human reluctance, the feeling of a careful man who has glimpsed something he is not at all sure he wants to be true. The same temporary trick that Planck meant to undo would become the foundation of everything that came next, and it took someone else, someone younger and far less attached to the old comforts, to look at Planck's packets and say the thing Planck himself could not bring himself to say, that they were real, that someone was Albert Einstein, and the year was 1905. It was an extraordinary year for him. A young man of 26, working as a clerk in a patent office in Bern, Switzerland, with no university post and no laboratory of his own, doing physics in the hours around his job. In that single year, he produced a handful of papers that would each, on its own, have secured his place in history. One explained the jittering dance of tiny particles suspended in fluid, and in doing so gave some of the firmest evidence that atoms are real. One laid the foundations of his theory of relativity and the relationship between mass and energy. And one was about light. That paper on light took Planck's reluctant little packets and treated them with complete and fearless seriousness. Einstein proposed that light does not merely get emitted in packets as some quirk of warm objects. He proposed that light simply is packets, that a beam of light is, in its true nature, a stream of discrete bundles of energy, each one carrying an amount set by its frequency, exactly as Planck's formula described, but as a real, physical fact about light itself, everywhere, always, whether it is being made or absorbed or simply crossing the void. These bundles would later be given a name. We call them photons. And Einstein had a perfect test in mind, an effect that had been quietly puzzling experimenters for years, and that the smooth wave picture could not explain. It is called the photoelectric effect. Shine light on a clean metal surface, and under the right conditions, the light will knock electrons loose, pulling them right out of the metal and into the space beyond. Simple enough to describe, but the details were maddening for anyone who believed light was a continuous wave. If light were a smooth wave, then a brighter light, carrying more energy, ought to knock the electrons out with more force, sending them flying away faster. And a dim light, given enough patience, ought to slowly pour in enough energy to free the electrons eventually, no matter what its color. Neither of these things happened. Instead, the experiments showed something strange and stubborn. Below a certain frequency of light, a certain threshold color, no electrons came out at all, no matter how blindingly bright you made the beam or how long you let it shine. A faint violet light could free electrons the instant it touched the metal, while an intense red light, vastly brighter, freed none whatsoever, not one, no matter how long you waited. And when light above the threshold did free electrons, turning up the brightness made more electrons come out, but it never made any single one of them faster. To make the freed electrons move faster, you did not need a brighter light. You needed a bluer one. In the smooth wave picture, this is nonsense. In Einstein's packet picture, it is beautifully, simply true. Picture each electron in the metal as needing one good knock to break free, a single push above a certain strength, with weaker pushes doing nothing lasting at all. Now picture light arriving not as a continuous wash, but as individual packets, each carrying an amount of energy fixed entirely by its frequency. An electron is freed when a single packet strikes it, and that one packet carries enough energy to do the whole job by itself. A red packet, low in frequency, is a weak knock, too weak to free the electron no matter how many of them arrive, because the electron deals with them one at a time, and 1,000 gentle taps delivered one after another still will not break a bond that needs a single firm blow. A violet packet, high in frequency, is a strong knock, enough to free the electron in one go. Make the light brighter, and you simply send more packets, more knocks per second, freeing more electrons, but each individual knock is exactly as hard as it was before, set entirely by the color. To hit harder, you must raise the frequency. You must change the color, not the brightness. That is the photoelectric effect, and that is why it could only be explained by light that comes in countable, frequency-sized pieces. there is a quiet irony worth pausing on, because it echoes Planck's own reluctance from the other side. An American physicist named Robert Millikan found Einstein's explanation so distasteful, so at odds with the cherished and beautifully successful wave theory of light, that he set out to prove it wrong. He was not a careless man. He was one of the most meticulous experimenters of his generation, and he spent the better part of a decade refining his apparatus, cleaning his metal surfaces in a vacuum, measuring with enormous care exactly how the energy of the freed electrons depended on the frequency of the light. He expected, year after year, to catch Einstein in an error, and his beautiful, patient work did the opposite of what he intended. It confirmed Einstein's photoelectric equation to remarkable precision, and along the way it gave one of the best early measurements of Planck's constant, the value coming out of the slope of his own carefully plotted data. The packets were real, demonstrated to be so by a skeptic who had devoted years to making them disappear. Even after his own results were in, Millikan remained uneasy about what they meant, and that unease tells you something true about how hard it was for everyone, even the people proving it, to let the smooth old lake go. In 1921, the Nobel Prize in Physics went to Einstein, and here is a detail many people find surprising. It was not awarded for relativity, the work he is most famous for today, the work that bent our whole idea of space and time. It was awarded specifically for his services to theoretical physics, and most especially for his discovery of the law of the photoelectric effect. The packet picture had become the official, prize-winning truth of physics, even as some of the deepest puzzles it raised, about how light could be a wave and a stream of packets at the same time, were only beginning to be felt. So let us gather the single most important rule out of all of this, because we will lean on it again and again for the rest of the night. It is the relationship Planck stumbled into and Einstein made real, and it can be written in a form so short that it almost looks too small to carry the weight it does. The energy of a single photon equals Planck's constant times the frequency of the light. E equals hf. That is the whole of it. Frequency is simply how rapidly the field oscillates as the ripple passes, how many times per second it rises and falls. And the rule says the energy of a photon depends on that and nothing else, not on how bright the light is, not on how far it has traveled, not on where it came from, only on its frequency, its color in the broadest sense, multiplied by that tiny fixed number, h. To feel it in your body rather than your head, imagine holding one end of a long, heavy rope, with the far end tied to a wall across the room, and you begin to flick your wrist. Flick it slowly, lazily, and you send long, loose, rolling waves down the rope, far apart and unhurried, one gentle hump following another. That is low frequency. That is red light, infrared, the gentle, low-energy end of things. Now flick your wrist faster and faster, and the waves crowd in tight against each other, rapid and close and quick, a dense procession of little crests. That is high frequency. That is blue light, ultraviolet, the energetic end. The energy carried by each ripple climbs in lockstep with how fast you shake your wrist. And here is the part that matters most. How hard you shake the rope, how big you make each wave rise and fall. That is the brightness, the number, and the size of the disturbances. And it is a completely separate thing from how fast you shake. You can send long, slow waves gently or fiercely, and they are still long, slow waves, still low frequency, still red. The energy of each individual photon lives in the frequency, in the rhythm of the shaking, in the F of that small and patient equation, and never in the mere vigor of it. Hold on to that rope for a moment longer, because it answers the question we left open at the very start, on the windowsill, with the warmth on the back of your hand. Where does the energy of light come from, if there is no fuel and no little glowing object to store it? It comes from the frequency. It comes from how fast the field was made to oscillate at the moment the ripple was first set going. A photon's energy was written into it at the instant of its birth, in the rate of that initial shaking, and it carries that energy faithfully across the entire universe without ever spending it, the way a single flick of your wrist travels the whole length of the rope without growing tired or fading away along the way. Which raises a lovely and natural question, one we are going to follow slowly into the next stretch of the journey. If every photon's energy is set at the instant it is born, fixed forever by the rate of that first shaking, then to understand the light we actually see, the colors of stars and flames, and the cold faint glow of distant clouds, we have to understand the bursts themselves. We have to ask what kinds of events out there in the cosmos shake the field, and how gently or how violently they do it, and what range of ripples they send streaming out across the dark toward us. That whole spectrum of births, from the softest radio whisper to the fiercest gamma flash, is waiting just ahead, and we will walk through it without hurrying a single step. So every photon's energy is set at the moment it is born, written into it as frequency, as the rate of that first shaking of the field. That single idea quietly sorts all of light into one great family, stretched out along a single long line from the slowest, gentlest ripples to the fastest, fiercest ones. We call that line the electromagnetic spectrum, and it is worth walking its full length slowly, the way you might stroll the length of a very long shoreline at dusk, because every kind of light you have ever encountered, and a great many you never will, live somewhere along it. They are all the same thing, the same self-renewing ripple in the same invisible ocean that Faraday felt and Maxwell described. They differ in one respect only, in how fast they oscillate, and therefore in how much energy each one carries. Let us begin at the gentle end, where the waves are long and slow and low in energy. These are the radio waves. Their ripples are enormous, sometimes meters from one crest to the next, sometimes far longer than that, stretching to the size of buildings and mountains and beyond. They oscillate lazily, unhurriedly, and so each radio photon carries only a tiny breath of energy. This is the soft murmuring end of the field, the long, rolling swells far out on the open water where the sea barely seems to move at all. It is also where Hertz first made light on purpose with his answering sparks, and it is the light that carries voices and music across whole cities, and it is the light by which radio telescopes listen, in enormous dishes turned up toward the night, to the faint and patient hum of distant galaxies. Gentle as it is, it crosses the universe just as faithfully as any other light, never tiring, never slowing. Walk a little further along the line and the waves draw in, growing shorter and a touch quicker. Now we are among the microwaves, ripples measured in centimeters. A little more energy in each one now, enough to set the water molecules in a bowl of food jostling and warming against one another. And there is one particular microwave glow we will return to right at the very end of our journey tonight, a faint and ancient light that fills all of space and carries the oldest message in the entire universe. But it is not time for that yet. For now, simply note where it lives on the line, here in the quiet microwave stretch, and let it wait for us. Onward, and the waves keep tightening, and we arrive at infrared. These ripples are shorter still, quicker still, And now the energy in each one is enough that we begin to feel it directly, as heat. This is the light your own warm body is glowing in at this very moment, pouring softly off your skin, invisible to your eyes, but plain as day to a thermal camera. Every warm thing radiates infrared, the embers in a dying fire, a sleeping animal curled in the dark, the whole dark side of the earth releasing the day's gathered heat back into space at night. It is the light of warmth itself, the glow of anything that holds a little heat. And then, in a band so narrow that it is almost startling how small it is, we reach the one part of the entire spectrum our eyes happen to be built to catch. This is visible light, and it is a thin little ribbon in the middle of an immense line. If the whole electromagnetic spectrum were laid out as a journey of many miles, the part we can actually see would be a single short stride, no more. And yet, within that one stride lies every color you have ever seen in your life. At the long, slow, lower energy edge sits red. As the ripples tighten and quicken, the color shifts gently to orange, then yellow, then green, then blue, and finally to violet at the short, fast, higher energy edge. A rainbow is nothing more than this narrow stretch of the spectrum pulled apart and laid out in order, the field's ripples sorted from the slow red swells to the quick violet ones by the raindrops in the air. It is humbling, in a gentle way, to realize how little of the whole we were ever given eyes for. We evolved beneath a particular star, and we evolved to see the narrow band of light that star pours out most strongly, the band that passes most easily through our air and our water, and we called that band the visible world, and for the whole of our history we quietly believed it was nearly everything there was. It was almost nothing. Past violet, the waves keep tightening beyond anything an eye can follow, and we cross into ultraviolet. More energy now in every photon, enough to begin doing real work and real damage, enough to burn skin on a bright afternoon, and enough to help the body make vitamin D. Further still, and we reach the X-rays, ripples so short and so quick and so energetic that they pass clean through soft flesh and are slowed only by denser things like bone, which is exactly why we use them to look inside ourselves without ever opening the skin. And at the very far end, the shortest and fastest and most energetic light there is, we arrive at the gamma rays. These are born only in the most violent events the universe knows how to make, in the hearts of exploding stars and in the churning regions around black holes, and a single gamma photon can carry more energy than 1 trillion of those gentle radio photons we started with at the other end of the shore. That is the whole line, from the longest, slowest radio swell to the sharpest gamma flash. And here is the thing to hold on to as we stand at the end of the shore and look back along all of it. Every single one of these is the same kind of ripple in the same field. None of them is more truly light than any other. Radio and gamma are not different substances, only the same disturbance shaking at wildly different rates. The only difference between them, the entire difference, is the frequency, the speed of the shaking, the F in that small equation from before. Which means that if we want to understand the light coming to us from any object anywhere in the sky, the question is always, every time, the same one. What event out there shook the field, and how violently? And so, where along this great line did the ripple it sent us begin its life? This is the heart of it, and it is so simple that it can slip right past you. A photon inherits its energy from its birth event. It is not handed a color at random. The violence or the gentleness of whatever made it is recorded permanently in its frequency, sealed in at the moment of its making, and it carries that record unchanged, across whatever distance and whatever silence lie between there and here. The light is a message about its own origin. To read the light, then, is to witness the event that made it, however far away that event was, however long ago it happened. And nature, it turns out, has only a small number of favorite ways to make light, a handful of birth events that produce nearly all the photons filling the cosmos. We are going to look closely at one of the most beautiful of them, the one happening inside every atom, everywhere, all the time, including inside the atoms of your own resting hand. But before the explanation came the clues, and the clues arrived a full century before anyone could make sense of them. In the early 1800s, a German optician named Joseph von Fraunhofer was making the finest glass instruments in the world. He was an orphan who had survived the collapse of the workshop he was apprenticed to, pulled alive from the rubble, and he had risen to become a master of lenses and prisms. Around 1814, working to perfect his glass, he passed sunlight through a fine slit and a prism, and spread it into the broadest, cleanest rainbow anyone had yet produced. And there, scattered across the smooth band of colour, he found something nobody expected. Dark lines. Narrow gaps where the colour simply went missing, as if someone had drawn fine black pencil strokes across the rainbow at very particular places. He counted them carefully, hundreds of them, and he mapped where each one fell, and he labelled the strongest with letters that astronomers still use today. He did not know what they were. He only knew, with the precision of a great instrument maker, exactly where they sat. The sun's light had a pattern of absences written into it, and Fraunhofer had drawn the first careful map of that pattern without any idea of what it meant. The meaning came decades later, around 1859 and 1860, from two more Germans working together, the physicist Gustav Kirchhoff and the chemist Robert Bunsen, whose name survives on every laboratory burner. They had a clean, hot, nearly colourless flame from that burner, and they began dropping pinches of different substances into it and spreading the resulting light through a prism. And they found that each chemical element, when heated, glowed with its own particular set of bright-coloured lines, sharp and specific, in a pattern that no other element shared. Sodium gave a certain pair of yellow lines, always in the same place. Other elements gave their own unmistakable patterns. Then came the discovery that tied it all together. Kirchhoff noticed that the bright yellow lines that sodium emitted fell at exactly the same places as one of the dark line pairs Fraunhofer had mapped in the sun. A glowing gas emits light at certain colors. A cooler gas, with light passing through it, absorbs light at those very same colors. The dark lines in the sun were the fingerprints of elements in the sun's own outer atmosphere, absorbing their signature colors out of the light streaming up from below. Fraunhofer's mysterious black strokes were a list, in code, of what the sun is made of. For the first time in history, a person could learn the composition of a body they could never reach or touch or sample, simply by reading its light. It is hard to overstate how astonishing that should have seemed. There had been serious thinkers who declared the chemical makeup of the stars to be the one thing humanity could never possibly know, forever beyond reach. And within a few years of that pronouncement, the answer was sitting in a prism on a laboratory bench, waiting to be read. Still, no one yet knew why each element made its own particular pattern. The fingerprints worked, but no one could say what drew them. The first crack of understanding came, charmingly, not from a famous physicist, but from a Swiss schoolteacher named Johann Balmer in 1885. Balmer was fascinated by the 4 visible lines of hydrogen, the simplest element of all, and he played with their measured wavelengths like a puzzle until he found a single tidy formula, a piece of arithmetic that produced all four of them exactly. He had no idea why his formula worked. It was a pattern he had simply uncovered in the numbers, a hint that something orderly and lawful lay underneath. And the longest, reddest, brightest of those four hydrogen lines, the first in his series, sat at a wavelength of about 656 nanometers, a deep and gentle red. It would take another generation, and a young Danish physicist, to explain why Balmer's formula was true. For that, we come to the year 1913, and to Niels Bohr. By Bohr's time, it was known that an atom was something like a tiny solar system, a dense positive nucleus at the center with negative electrons somewhere around it. But there was a deep and troubling problem, and it was, at root, the very same problem we are going to meet again in the next part under a different name. According to the classical physics of Faraday and Maxwell, an electron circling a nucleus is an accelerating electric charge, because anything moving in a circle is constantly changing its direction, and an accelerating charge must radiate away light, and radiating away light means losing energy. By that flawless-looking logic, every electron in every atom should pour out light, lose its energy, and spiral inward to crash into its nucleus in a fraction of a second. All matter, everywhere, should instantly collapse into nothing. Plainly, it does not. You are made of countless atoms that have held themselves quietly together for billions of years. Bohr's answer was as bold as Einstein's had been with the packets. He proposed that the electrons are simply not free to orbit at just any distance the way a planet can sit at any distance from the sun. Instead, he said, an electron in an atom can only occupy certain specific orbits, certain allowed rungs, with nothing in between them. Just as Planck's energy came only in fixed packets, the orbits themselves came only in fixed steps. An electron sitting on one of these allowed rungs is stable, and against all the classical reasoning, simply does not radiate at all, which is the rule Bohr had to lay down to keep atoms from collapsing. But an electron can jump from one rung to another. And that jump, that single small act, is one of the great light-making events of the entire universe. Picture the allowed orbits as the rungs of a ladder, with the lower rungs nearer the nucleus and the higher rungs further out. A lower rung is a lower energy place for the electron to be, a higher rung a higher energy one. When an electron sitting on a high rung drops down to a lower one, it suddenly finds itself with energy to spare, exactly the difference in energy between the two rungs, no more and no less, and it sheds that surplus in the only way it can. It emits a single photon, and that photon flies off carrying precisely the energy of the gap between those two rungs. Because the rungs are fixed, the gaps between them are fixed, and so the photon's energy is fixed, which means, through E equals hf, that its frequency is fixed, which means in the end that its color is fixed. A given jump between two given rungs in a given kind of atom always produces light of exactly the same shade, every single time, in a flame on Earth and in a star 10,000 light years away. And now Balmer's mysterious formula suddenly made perfect sense. His four visible hydrogen lines were simply four particular jumps, electrons in hydrogen falling from various higher rungs down to one specific rung, the second one up. That deep red line at 656 nanometers, the brightest of them, was the gentlest of those falls, the drop from the third rung to the second. Astronomers gave it a name. They call it hydrogen alpha, and it glows in exactly that deep soft red you see in the great photographs of star-forming clouds, the rose-colored nebulae where new stars are being lit. That precise red is hydrogen announcing itself. The same jump, the same gap, the same color, in a sealed tube in a laboratory, and in a cloud of gas so far away its light set out before there were cities on the earth. Sit with what this gives us, because it is one of the quiet miracles of science. It means the light arriving from a star is not just a glow to be admired. It is an itemized list. Spread a star's light out into its full rainbow with an instrument called a spectrograph, and you find it is not smooth at all. It is crossed by sharp, specific lines, bright where certain atoms are emitting their signature colors, and dark where certain atoms are absorbing them, exactly the lines Fraunhofer first mapped in the sun. And because each pattern belongs to one element and one element only, as unmistakable as a fingerprint, we can read, in the light of a star, we will never visit and never touch, precisely what it is made of. Hydrogen, helium, carbon, the iron forged in its core, all of it spelled out in the spacing and the strength of the lines. This is how we know the composition of objects unthinkably far away. The atoms wrote their names into the light at the moment they made it, and the light carried those names faithfully across the void, and we slowly learned how to read the handwriting. It is the entire foundation of how the great telescopes do their work even now. The James Webb Space Telescope, which launched at the very end of 2021, and drifts at its station far beyond the moon, 1,000,000 miles out on the cold side of the Earth, does exactly this. It gathers the faint infrared light of the most distant and ancient galaxies and spreads it into spectra, reading the fingerprints written in it, and it does something Fraunhofer could only have dreamed of. When a planet circling another star passes in front of that star, a little of the starlight filters through the planet's thin ring of atmosphere on its way to us, and the gases of that distant air absorb their own signature colors out of it, leaving their fingerprints behind. Webb reads those fingerprints, teasing apart the colors to find the signatures of water, of carbon dioxide, of the molecules drifting in the skies of worlds we will never reach. Every one of those discoveries traces straight back through Bohr to Balmer to Fraunhofer, to the simple and beautiful fact that an electron falling between two fixed rungs makes light of one fixed color, and that color is a name. But the falling electron is not nature's only way of making light. There is another, born not from a neat jump between rungs, but from sheer raw motion, from charges shaken and bent and braked in the open, and it carries us straight back to the very problem Bohr had to step around, the accelerating charge that classical physics said must always radiate. We set that problem aside a moment ago to keep the atoms from collapsing. Now we can pick it up again, gently, because out in the wider universe, it turns out to be not a problem at all, but the source of some of the most spectacular light in the entire sky. That is where we are going next, and there is no hurry to get there at all. Recall the old worry, the one Bohr had to step around to keep the atoms of the world from collapsing. An accelerating electric charge radiates light. Anything that changes a charge's speed or its direction shakes the field around it, and the field answers by sending out a ripple, a photon, carrying away some of the charge's energy. Bohr's electrons escape this fate only because their allowed orbits are special and stable, protected by the strange new rules of the quantum world. But a free charge, one not bound onto a quantum ladder, one simply moving through open space, obeys the old classical rule completely and faithfully. Whenever you take a free electric charge and accelerate it, force it to speed up or slow down or swerve, it sheds light, and the energy of that light is set, as it always is, by how violently the charge is shaken. Out in the wider universe, there are two grand ways this happens, and both of them occur in some of the most extreme and beautiful places that exist. The first is what happens when a charged particle is forced to curve. Imagine an electron moving very fast, close to the speed of light, and now imagine it entering a region threaded with a strong magnetic field. A magnetic field does not speed a charge up or slow it down directly. What it does is bend its path, push it sideways, curl it around. And so the fast electron, instead of flying straight, is wound into a tight spiral, whipped around and around the magnetic lines of force, turning and turning. But turning is acceleration. A constant change of direction is a constant acceleration, even if the speed never changes. And so the spiraling electron, forever curving, pours out light continuously as it goes, flinging photons off the outside of every turn the way water flies off a spinning wheel. We call this synchrotron radiation, named for the particle accelerators here on Earth where it was first clearly seen and studied, machines in which electrons are driven in great circles and shine brilliantly simply because they are being bent. In space, this same process plays out on an enormous scale, wherever fast charged particles meet strong magnetic fields, and the result is some of the most striking light in the sky. And there is one object that shows it more clearly and more famously than almost any other, an object worth pausing on because its whole story is woven from the ideas of this evening. In the year 1054, astronomers in China and observers in other parts of the world recorded a startling new star that appeared suddenly in the sky. It blazed so brightly that, by the careful records kept at the time, it was visible in broad daylight for the better part of 3 weeks, and remained visible at night for nearly 2 years before slowly fading from view. What they had witnessed, though they could not have known it, was a supernova, the cataclysmic death of a massive star, a star that had run out of fuel and collapsed and detonated, briefly outshining whole galaxies. Centuries later, when astronomers turned their telescopes to that same patch of sky, in the constellation we call Taurus, they found the wreckage still expanding, a tangled, glowing cloud of shredded gas that we now call the Crab Nebula. The debris of that ancient explosion still rushing outward almost 1,000 years on. And at the very center of that cloud sits what is left of the star's crushed heart, a neutron star, the collapsed core, an object so dense that a sugar cube's worth of its material would weigh about as much as a mountain. This particular one spins extraordinarily fast, turning on its axis roughly 30 times every second, and as it spins, it sweeps beams of radiation around like a lighthouse, flashing at us with each turn. We call such a spinning, flashing neutron star a pulsar. It drags an immense magnetic field around with it as it whirls, and it flings out a wind of electrons traveling at very nearly the speed of light. Those electrons, caught in that powerful spinning magnetic field, are bent into tight spirals, and as they curve, they blaze with synchrotron radiation across the whole spectrum, from radio waves to visible light to X-rays and beyond. The eerie, ghostly bluish glow that fills much of the Crab Nebula in photographs is precisely this, the light of countless electrons being forced to curve in a magnetic field, shining simply because they cannot fly straight. 1,000 years after the star died in fire, its corpse still lights the cloud around it, with the radiation of bending charges. Much of the strange structured light we gather from across the universe is this same synchrotron glow, the radiation of charges trapped and wheeling in magnetic fields. It pours from the regions around neutron stars and from the vast jets that active galaxies fling out across millions of light years, electrons spiraling in cosmic magnetism and shining as they turn. And every photon of it carries, in its frequency, the record of how hard those electrons were bent, the violence of the curving written permanently into the light. The second great way that raw motion makes light happens not when a charge is bent, but when a charge is braked. Imagine an electron racing through hot, thin, ionized gas, the kind of searing plasma found near a black hole or in the heart of a cluster of galaxies, a place where atoms have been stripped of their electrons and the bare nuclei drift about freely. As our fast electron flies past one of those heavy, positively charged nuclei, the nucleus tugs at it, deflects its path, and drags hard at its motion, decelerating it sharply in an instant. And that sudden braking is itself a fierce acceleration, a violent change of motion, and so the electron sheds the energy it loses as a photon, flung off at the moment of the swerve. The German name for this, kept by physicists in every language, is Bremsstrahlung, which means simply braking radiation. It is light born from the slowing of a charge, and it pours out of the unbelievably hot plasma swirling down toward black holes, where infalling gas is heated to millions of degrees as it crowds inward, and from the immense clouds of hot gas that fill the spaces between galaxies in great clusters, gas so hot it glows in X-rays across regions millions of light years wide. So we now have gathered together the small handful of ways that nature makes nearly all the light in the cosmos. There is the falling electron in Bohr's atom, dropping between fixed rungs and emitting its one fixed color, the source of every spectral fingerprint. There is the spiraling electron near a neutron star, bent by magnetism into endless curves and blazing with synchrotron light. There is the braking electron beside a black hole, swerving past a nucleus and flinging off a photon as it slows. And there is, as we saw at the very heart of all this, the simple thermal glow of any warm thing, the embers and the iron and the surface of the sun, radiating because their charged particles are jostling with heat. And notice, as you rest, the quiet unity running underneath every one of them. In each case, without exception, the recipe is exactly the same. A charge is disturbed, the field ripples in response, and a photon is born carrying the energy of that disturbance written into its frequency. A gentle disturbance makes a gentle, low-energy photon, one of the long radio swells. A violent disturbance makes a violent, high-energy photon, one of the sharp gamma flashes. The character of the birth is preserved perfectly in the child, sealed in at the instant of making and carried unchanged across the whole of space. That is the single thread that ties the warmth of a candle to the glow of an exploded star, that links the light from your bedside lamp to the radiation of a black hole's burning disk. They are all the same act, performed gently or fiercely, a charge shaken, and the field answering. And that is why, when we look out at the night sky across all the different bands of light, in radio and infrared and visible and X-ray and gamma, we are really looking at a vast catalogue of events, an immense library of disturbances. Each kind of light tells us about a different kind of shaking, a different birth, a different drama. The radio whisper of a cold gas cloud, the infrared warmth of dust around a forming star, the visible fingerprint of hydrogen in a stellar atmosphere, the X-ray scream of gas falling into a black hole. We do not have to travel to any of these places to know them. We only have to gather their light and read what was written into it at the moment of its making. There is something deeply steadying in that, as you lie here in the quiet dark. All the fierce machinery of the cosmos, the spinning neutron stars, and the devouring black holes, and the stars that tore themselves apart 1,000 years ago, all of it reaches us only as light, only as faint ripples in the field that have travelled in perfect silence for hundreds or thousands or millions of years to arrive, softened by all that distance, at the lens of a telescope or the back of a wondering eye. The violence itself stays out there, unimaginably far away, long finished. What comes to us, what actually crosses the dark and touches us, is only the message, carried gently, the field still rising and falling exactly as it has since the event that set it going, however long ago that was. The Crab Nebula's glow left it more than 6,000 years before it reaches our telescopes, the light of bending electrons crossing all that space to arrive only now. The explosion that lit it was seen in our skies in 1054, but the cloud itself lies far enough away that we are always looking at its distant past, never its present. By the time you read what light tells you, the telling is already old, and yet there it is, faithful, undimmed in its message, the curving of those electrons preserved across 60 centuries of travel and delivered intact to us. And the most patient message of all comes from the nearest star of them all, our own sun, where a single photon born in the core can spend a length of time that beggars belief simply trying to escape its own birthplace, long before it ever begins the easy 8-minute sprint to your window. That long, slow, almost unimaginable journey out of the heart of a star is where we are going next, and there is no hurry to get there at all. The warmth on the back of your hand took a little over 8 minutes to reach you, crossing the gulf between the sun and the earth at the speed of light. We said as much at the very beginning, and it is true, but it is only the last easy chapter of a far longer story, because that 8-minute crossing of empty space is nothing at all compared to the journey the light made before it ever left the sun. The hardest part of a photon's life, the part that can last longer than our entire species has walked the earth, happens before it escapes its own birthplace. To feel why, we have to go down slowly, all the way down into the core. At the very center of the sun, the pressure is beyond anything we can picture, and the temperature reaches around 15 million degrees. Down there, in that crushing heat, hydrogen is being fused into helium, the slow nuclear furnace that powers the star and has powered it for 4.5 billion years. It does not happen all at once, in a single step, but through a patient chain of small encounters. Protons, the bare nuclei of hydrogen, collide, and now and then, against enormous odds, two of them stick together and one transforms, and step by step, through a sequence physicists call the proton-proton chain, 4 hydrogen nuclei are eventually built up into a single nucleus of helium. And here is the quiet accounting that matters. The helium that results weighs very slightly less than the 4 hydrogen nuclei that went into making it. A tiny sliver of mass, less than 1% of what went in, has gone missing somewhere in the building. That missing mass does not simply vanish. It is released, as we will come to understand more fully before this section is done, as pure energy, and a great deal of that energy is born as light, as gamma rays, the sharpest and most energetic ripples on the entire spectrum, the violent children of a violent birth deep in the solar core. There is a poignant detail worth holding here. Some of the energy of each fusion reaction departs not as light, but as a ghostly particle called a neutrino, and the neutrino, barely interacting with anything at all, flies straight out of the sun at almost the speed of light, and reaches the Earth in those same 8 minutes, having passed through the entire body of the star as though it were not there. The neutrino escapes instantly. The photon, as we are about to see, does not. 2 children of the same reaction, born in the same instant in the same place, and one of them will be free of the sun before the other has traveled the width of a coin. Because picture one of those gamma photons, newly made in the core, beginning its journey toward the surface and toward, eventually, your window. You might imagine it racing straight out, covering the radius of the sun in a couple of seconds, since after all it travels at the speed of light, the fastest thing there is. It does not. What happens instead is one of the strangest and most humbling facts in all of solar physics. The interior of the sun is so unimaginably dense, so tightly packed with particles, that a photon cannot travel any meaningful distance at all before it slams into something. It is absorbed by a particle almost the instant it is born, after crossing a gap that may be no wider than the breadth of a fingernail, and then, a moment later, it is spat back out again in some entirely new and random direction. It might be flung outward, toward the surface and toward freedom. It might just as easily be flung straight back down, deeper toward the core it just came from. Then it crosses another tiny gap and is absorbed and re-emitted yet again, in another random direction, and again, and again, and again, endlessly, for an unimaginable length of time. This is what physicists call a random walk, and it is exactly as aimless as it sounds. The photon, or more honestly the parcel of energy, for it is absorbed and reborn so many countless times that no single original photon survives the trip unchanged, staggers through the dense interior of the sun like someone trying to cross a vast, crowded, pitch-dark ballroom, by taking one short step, being spun around blindfolded, taking another short step in whatever direction they happen to be facing, being spun around again, with no sense whatsoever of which way the exit lies. Each individual step happens at the full speed of light, but the steps go nowhere on average. They cancel each other out, a step outward undone by the next step inward, so that the net progress toward the surface is agonizingly, almost unbelievably slow. Exactly how slow is genuinely difficult to state with precision, and an honest guide will tell you so. The estimates vary widely depending on the assumptions you make about the density and the opacity of the sun's layers, ranging from something like 10,000 years to a few 100,000, with the figures of around 100,000 years often quoted as a reasonable middle. The exact number matters far less than the sheer scale of the thing. So take it in gently, the way you would take in the size of a mountain by looking at it rather than measuring it. The energy now arriving as sunlight, resting on your skin this very moment, may have begun its long climb out of the solar core back when our distant ancestors were first learning to shelter fire and shape stone tools. It has been bouncing blindly through the body of the sun for the whole span of recorded human history, and very much longer than that, on a walk so slow that whole civilizations rose and flourished and fell on the earth in the time it took that energy to inch its way from the center to the surface of a single star. And along that endless staggering walk, something else happens to it, something gentle and important. With every absorption and re-emission, the energy is shared out and divided a little, handed off and split among more and more particles, so that the single fierce gamma photon born in the core does not emerge from the sun as a gamma photon at all. Each violent gamma ray is, over those thousands of years, gradually broken down into a great many gentler, lower energy photons. By the time the energy finally nears the surface, the sharp violence of its birth has been smoothed almost entirely away, softened down into the warm yellow-white light of ordinary sunshine. The light that warms you is the great-great-grandchild, many times over, of that original gamma ray, gentled by 100,000 years of patient bouncing into something a living creature can stand beneath and cool pleasant, can lie in on a summer afternoon and cool rest. Then, at last, near the outer layers of the sun, the character of the place changes. The plasma thins enough that the energy can finally be carried not by that maddening bounce, but by the bulk churning of the gas itself. Vast columns of hot material rising toward the surface, cooling and sinking back down. A great slow boil, like the rolling of water in a pot just before it simmers. This final convective stretch takes mere weeks or months, a blink compared to what came before. And then the energy reaches the visible surface, the photosphere, and the light breaks free at last into open space. After all those thousands of years of going essentially nowhere, the very last leg of the journey, the 93 million miles across empty space to the Earth, takes a little over 8 minutes. A straight, clean, effortless sprint through the dark. The hardest part was never the great distance to us. The hardest part was getting out of the sun at all. There is a spacecraft that has flown closer to that fierce outer edge than anything humanity has ever built, and it has become something of a recurring companion on this channel, so it is worth pausing on. NASA's Parker Solar Probe launched in 2018, and it was given a task that sounds almost like a dare written into a mission plan. It was sent to fly directly into the sun's outer atmosphere, the corona, that faint and strangely, searingly hot crown of plasma that surrounds the star, far hotter than the visible surface below it, for reasons solar physicists are still working to fully understand. In 2021, it did exactly that, becoming the first spacecraft in history to fly through the corona, to pass within the sun's own atmosphere and emerge again intact. It is protected by a thick carbon heat shield that takes the full fury of the sun on its forward face, while the instruments shelter in its shadow, kept relatively cool just behind it. And it moves astonishingly fast, faster than any object people have ever made, whipped to enormous speed by the sun's gravity as it swings close, drawing nearer with each successive orbit. It is a strange and moving thing to picture. A small machine of ours, built on a planet 93 million miles away, dipping again and again into the outer reaches of the very star that has fed every living thing that has ever existed, sampling and listening at the place where that 100,000-year journey finally, quietly ends. Let that settle for a moment, before we turn to the deeper question waiting underneath all of it. Because we said something in passing a little while ago that deserves to be opened up slowly, since it is, in a sense, the truest answer to the question we began with tonight. We said that when hydrogen fuses into helium, a little mass goes missing, and that the missing mass is released as energy and light. This is the most direct answer there is to where light energy comes from. Sometimes it comes, quite literally, from mass itself, from matter ceasing to be matter and becoming light instead. This is the real meaning of the most famous equation ever written, Einstein's E equals mc squared. People recite it constantly, almost as a kind of charm, and yet its actual message is easy to let slip past. It does not merely say that mass and energy are related, that one can be traded for the other at a rate. It says something far deeper. It says that mass and energy are not two different things at all. They are, at the bottom of everything, the same single thing, two faces of one underlying quantity, and so one can be converted into the other, the way water can be turned to steam. The c squared in the equation, the speed of light multiplied by itself, is an enormous number, which means that even the tiniest pinch of mass holds a staggering amount of energy locked up inside it. The small sliver of mass lost in each fusion reaction, multiplied by that vast factor, is the source of all the sunlight that has ever fallen on the earth, all the light that has warmed every ocean and grown every forest across billions of years. The sun is, slowly and continuously, turning a portion of its own substance into light. It is converting some 4 million tons of its mass into energy every single second, and it has been doing so with barely a flicker for the entire history of life on this planet, and it has fuel to continue for billions of years more. But fusion, for all its grandeur, is only a partial conversion. Most of the mass remains behind, bound up now as helium. There is, however, a process in nature that takes the very same idea all the way to its limit, that converts matter into light completely, with absolutely nothing left over at all, and it is perhaps the purest answer to our question that physics has to offer. For that, we need antimatter. Every kind of particle in the universe has a mirror image twin, an antiparticle, identical to it in mass, but opposite in certain properties such as electric charge. The electron, that small negative particle we watched falling between Bohr's rungs, has a twin called the positron, exactly as heavy but carrying a positive charge instead of a negative one. Antimatter sounds like the invention of a storyteller, but it is entirely, ordinarily real. It was predicted, remarkably on paper before anyone had seen it, by the physicist Paul Dirac at the very end of the 1920s. Dirac was trying to write an equation for the electron that respected both the quantum world and Einstein's relativity, and his equation insisted, almost against his will, that a second kind of particle must exist, the electron's positive twin, emerging unbidden from the mathematics, much as light itself had once emerged unbidden from Maxwell's. And then it was actually found. The positron was spotted in cosmic ray experiments by Carl Anderson in 1932, real tracks of a real particle curving the wrong way in a magnetic field. The prediction had been right. Antimatter exists, and it is made naturally, even now, in many violent corners of the cosmos, and even in small amounts in certain kinds of radioactive decay here on Earth. Now here is what happens when a particle of matter meets its antimatter twin. When an electron and a positron drift into one another, they do not bounce apart, and they do not merge into some new, heavier particle. They annihilate. Both of them vanish completely, the whole of their mass gone in an instant, and in their place, conserving everything that the laws of physics require to be conserved, there appear two photons, flying apart in opposite directions. The entire mass of both particles has been converted, totally and without the smallest remainder, into pure light. And because the mass that was destroyed is precisely known, the energy of each of those photons is precisely known too, a sharp and specific gamma-ray signature. Astronomers have a name for the particular energy it produces, and they can recognize that exact gamma-ray line wherever in the sky matter and antimatter are meeting and unmaking each other. There is, in fact, a faint and steady glow of exactly this light, coming from the central regions of our own galaxy. A soft signal that somewhere in toward the heart of the Milky Way, positrons are meeting electrons and turning into light, though precisely what is making all those positrons remains an open and genuinely debated question. Sit with the completeness of that, here in the quiet. In fusion, the sun gives up only a sliver of itself to light, holding the rest back as helium. In annihilation, matter gives up the entire whole of itself, all of it, keeping nothing in reserve. Two solid particles, each with a definite mass, each as real and as substantial as a mote of dust, touch one another, and in that single instant they cease to be matter at all, and become two ripples in the field, two photons racing off into the dark in opposite directions. The mass does not shrink or fade or hide itself away. It is converted fully and exactly and without loss into light. And so the question that opened this whole journey, the quiet contradiction resting on the windowsill, where does massless light get its energy from, finds one of its very deepest answers right here. Sometimes the energy of light is quite simply mass that used to be. The warmth on your hand is partly the sun spending its own body, 4 million tons of itself each second, across the long ages, and the sharpest light in the whole cosmos can be matter and antimatter, erasing one another completely and leaving behind only the field, still rising and falling, still carrying away everything those particles used to be. There is something almost consoling in it, lying here in the dark with the day behind you. Nothing is ever truly lost. The mass that vanishes does not fall out of existence and into nothing. It only changes its clothing and travels on as light, weightless now and free, able to cross the entire universe and warm a hand, or register on a telescope 1 billion years from now, in some place that does not yet exist, for some eye that has not yet opened. Matter becomes light, and light carries the faithful memory of the matter it once was, across any distance and any silence you could ever name, which leaves us with one last quiet puzzle, hanging there in the dark, and it is a lovely one to drift toward. We have spoken all night as though light has no mass, and it does not, and yet we have also said more than once that light can push, that it leans on a sail, that it nudges a spacecraft gently forward across millions of miles. How can something with no mass shove anything at all? How can a weightless ripple deliver a push you can actually measure on an instrument? That gentle paradox, the push of the weightless, is exactly where we are heading next, and we will get there slowly, in no hurry whatsoever. We have spent all night standing on a single fact, that light has no mass, and we have watched it carry energy across the whole spectrum, inherit that energy from the violence or the gentleness of its birth, and even arrive as mass that used to be matter. But there is a second fact about light that seems at first to sit in flat contradiction to the first. Light can push, not in some abstract mathematical sense, not as a figure of speech. It can press on a real surface with a real force, nudge a real object forward, and in the right circumstances carry a spacecraft clear across the solar system with no fuel at all. And the question this leaves us with is sharp and simple and worth turning over slowly. How can something with no mass push on anything? The trouble is that we learn about pushing in a world of solid things. A push in everyday life means one massive object striking another. A rolling ball knocks another ball forward across the felt. A hand presses a heavy door open. A wave of water shoves a boat up the beach. In every one of these cases, the thing doing the pushing has mass, and it has motion, and the combination of the two is what physicists call momentum, the quantity of motion a moving object carries, the thing that lets it shove whatever it happens to meet. For most of the long history of physics, momentum was understood as exactly that. Mass multiplied by velocity, the heaviness of a thing times the speed of its travel. And by that understanding, the rule is plain. No mass means no momentum, and no momentum means there is nothing there to push with at all. By that reasoning, light should be utterly, completely powerless to move anything. It should glide through the room and press on nothing whatsoever, a thing made of pure brightness and no force. And yet it does press. So the everyday formula, useful as it is, must somehow be incomplete. The fuller truth comes once again from Einstein, and from the very same body of work that gave us E equals mc squared. That famous little equation, it turns out, is only a fragment, the simplified corner of a larger and more honest relation. The complete version says that the energy of a thing, squared, is equal to its momentum times the speed of light, that whole quantity squared, added to its mass times the speed of light squared, that quantity squared as well. It looks forbidding written out in full, and there is truly no need to carry any of the algebra into the dark with you tonight. What matters, the only thing that matters, is the shape of what it says, because the shape is beautiful, and once you see it, the paradox simply dissolves. The relation says that a thing's energy can have two separate sources. One source is its mass. The other source is its momentum, the energy carried in motion itself. Now think about what this means for an ordinary object sitting perfectly still. It is not moving, so its momentum is zero, and the whole momentum part of the relation falls away to nothing, leaving only the mass part behind. And what is left, when you set the momentum to zero, is precisely the famous E equals mc squared, energy entirely from mass. That is the corner everyone knows, the special case of a thing at rest. But now ask the opposite question. What happens for a thing that has no mass at all, like a photon? Set the mass to zero, and now it is the mass part of the relation that falls away to nothing, leaving only the other part behind, the part that comes from momentum. The energy of a massless thing comes entirely from its momentum. And read the other way around, that same statement says that a massless thing which carries energy must carry momentum. It has no choice in the matter. The very same relation that binds mass to energy also says, in the very same breath, that energy and momentum are bound together whether or not any mass is present at all. So here, gently, is the resolution to the whole paradox. Light has no mass, and therefore it has none of the kind of momentum we learn about as children, the mass times velocity kind. But it most certainly has energy. We have spent this entire night establishing exactly that. And energy carries its own momentum directly, with no need to borrow any from mass whatsoever. A photon's momentum is simply its energy divided by the speed of light. The more energy a photon carries, the more momentum it carries, and the harder it can push on whatever it strikes. The push was never about mass at all. We had only ever seen the one special case, the familiar world of slow and heavy objects, and we had quietly mistaken that special case for the whole of the rule. Momentum does not require mass. It only requires energy in motion, and light is precisely that, energy in motion, never resting, never anything else. Take that in slowly, because it overturns something most of us assumed, without ever once noticing that we had assumed it. Every photon arriving from the sun carries not only energy to warm you, but momentum to push you, ever so slightly. The sunlight resting on your skin is, in the most literal and physical sense, leaning on you, pressing you very gently toward the ground. The push is unimaginably faint, far too soft for any nerve in your body to feel, far too small to stir a feather. But it is real, and it is measurable, and across large enough surfaces and long enough spans of time, it becomes a genuine force that engineers are obliged to take seriously. It took a remarkably long time to measure, precisely because it is so faint. The prediction that light should exert a pressure went all the way back to Maxwell himself, falling naturally out of his electromagnetic theory in the 1870s. But predicting a feather-light force on paper and actually catching it in a laboratory are two very different things. There was even a famous false trail along the way, a device called the Crookes radiometer, which you may have seen, a little glass bulb holding a set of vanes that are black on one side and shiny on the other. mounted so they can spin freely. Put it in sunlight and the vanes turn, and for a while people believed they were watching the pressure of light pushing the vanes around directly. They were not. The truth was subtler and almost the reverse. The vanes turned because of the faint warming of the thin traces of gas left inside the bulb against the dark sides of the vanes. The real pressure of light is so much gentler than that competing effect that, in the radiometer, it is entirely buried beneath it. The lesson was a hard and useful one. To measure the true push of light, you had to escape every other effect that could so easily masquerade as it. The first to truly do so, to measure the pressure of light itself in the laboratory, was a Russian physicist named Pyotr Lebedev, around the turn of the 20th century, in 1900. He built an exquisitely delicate apparatus, lightweight vanes suspended on a fine fiber so they could twist freely, and he shone carefully measured light upon them and managed to detect the tiny twist as the light pressed against the surfaces. He had to fight against every competing influence, the faint warming of the surrounding air, the slightest stray current, the very effects that had fooled the watchers of the radiometer, all of which threatened to swamp the whisper-soft signal he was hunting. But through great care he separated them out, and he found it. He measured the genuine push of light, and the amount he measured matched what Maxwell's theory had quietly promised decades before. Light pressure was no longer a prediction sitting on paper. It was now a number you could read off an instrument on a bench. For a long while after that, it remained mostly a curiosity, a delicate and surprising fact for the textbooks. And then, much later, physicists began to wonder whether such a gentle and precise force might actually be put to work, whether the push of light might be exact enough to grip and hold and move the very smallest things. And it was here that one of the loveliest applications of the whole idea was born, in the hands of an American physicist named Arthur Ashkin, working at Bell Laboratories in the latter part of the 20th century. Ashkin realized that if light carries momentum, then a tightly focused beam of light could be used to take hold of a tiny object, a small transparent bead, a single living cell, even an individual bacterium, and to hold it suspended right in the beam, as if grasped by an invisible pair of fingers made of nothing but brightness. The radiation pressure of the focused light would gently trap the little particle at the brightest point of the beam and hold it there, and the beam could then be moved, carrying the particle with it, with the most exquisite delicacy, all without anything solid ever touching the object at all. He called the device optical tweezers, tweezers made out of light. It sounds almost like a conjurer's trick, picking up a living cell with a beam and setting it down again entirely unharmed. And yet it works reliably and precisely, and it became an indispensable tool across biology, letting researchers take hold of the machinery of life one single piece at a time, stretching a strand of DNA, measuring the minute force of a single molecular motor as it walks along inside a cell. The recognition for it was a very long time in coming. Arthur Ashkin was awarded a share of the Nobel Prize in Physics in 2018 for the optical tweezers and their application to biological systems at the age of 96, making him at that time the oldest person ever to receive a Nobel Prize. More than a century after Lebedev first felt light twist a suspended vane, the push of the weightless had become a way to cradle a single living cell in a beam of light. But the grandest demonstration of all is not found in any laboratory. It is out in space, where there is no air to interfere and no friction to fight against, where even the faintest, most patient push can build, over weeks and months, into real and useful motion. This is the long-held dream of the solar sail, a craft that carries no fuel and no engine of any kind, only a vast, thin, mirror-bright sheet, and that lets the steady pressure of sunlight press against that sheet and drive it forward through the void. For a long time it was an idea that writers and engineers loved dearly, but that no one had truly flown. The push of sunlight is so very slight that to make any use of it, you need a sail enormous in its area, and almost impossibly thin and light, and you need the patience to let an almost imperceptible acceleration accumulate, hour after hour, day after day. In 2010, the Japanese space agency, JAXA, flew the mission that proved it could really be done. It was called Icaros, and it was the first spacecraft in history to demonstrate solar sailing as its main means of propulsion in deep space. After its launch, it spun itself and gently unfurled a square sail roughly 20 meters across on its diagonal, a membrane only a handful of microns thick, thinner than a single strand of human hair, glittering as it spread open against the black on its long way toward Venus, and then it simply let the sunlight push. There were no rockets firing, no fuel burning anywhere aboard, nothing at all but the steady, silent rain of photons streaming out from the sun, each one weightless, each one carrying its own small parcel of momentum, striking the great thin sheet and pressing it ever so gently outward. And here is a detail that turns out to matter. When a photon bounces cleanly off a mirror surface, rather than simply being absorbed by it, it hands over even more push than it otherwise would, because it arrives carrying momentum in one direction and departs carrying momentum in the other, and the surface must account for the whole of that change. So a bright, reflective sail catches nearly twice the push of a dark, absorbing one. Across the whole vast area of the sail, across the countless trillions of photons striking it every single second, that feather-light pressure gathered itself into a genuine, continuous, measurable thrust. The force, by any everyday standard, was minute. The push from the sunlight amounted to something on the order of a small fraction of a gram of force across the entire sail, a force you could be entirely forgiven for calling nothing at all. Less than the weight of a few grains of rice resting in your palm. And yet, in the frictionless quiet of deep space, a push that never once stops, that presses on and on through every hour of every day and every week, does not need to be strong. It only needs to be patient. Icaros sailed on light, and it was even steered by light, for the craft could subtly change how its surface caught the sunlight, and so adjust its course without a drop of fuel, and it was carried across many millions of kilometers by the very same weightless ripples that warm the back of your hand on an ordinary afternoon. It was not the last of its kind either. Some years later, in 2019, a small organization of space enthusiasts called the Planetary Society flew a modest spacecraft of their own, called LightSail 2, into orbit around the Earth, unfurled its own bright sail, and successfully used the pressure of sunlight to raise the high point of its orbit, demonstrating once more, and now in the crowded skies just above our own heads, that a craft can change its path on nothing but light. The dream had become almost routine. Light could fly a ship. There is something quietly perfect about that image to hold as you rest tonight. A thin silver sail spread wide open in the dark and the deep silence, far from any world, drifting steadily forward on nothing whatsoever but light. No fuel, no sound, no engine of any kind. Only the oldest pressure in the universe, the gentle and tireless insistence of sunlight, pushing a small sliver of human cleverness slowly through the void. The very same light that took 100,000 years to claw its way out of the heart of the sun reaches that sail just 8 minutes later, and without any weight, without the faintest sound, leans against it and carries it on its way. And it leaves us, at the last, with the deepest question of the whole night, the one we have been circling toward since the very first words on the windowsill. We have learned that light has no mass, that it carries both energy and momentum, that it can be born from violence and born from matter itself, and that it can push a sail clear across the heavens. But why must it travel so fast, and only ever at that one single speed, never slowing, never resting, never at peace for even the smallest fraction of an instant? Why is the speed of light the speed of light? That final question, and the strange and beautiful answer that physics gives to it, is where our journey gently drifts to its close, and there is no hurry at all to arrive there. There is a question we have stepped around all evening, the way you might step around a deep pool in the dark, sensing it is there before you can quite see it. We have said, over and over through the night, that light travels at the speed of light, as though that were simply a fact about how fast it happens to go, like a car settling into a comfortable cruising speed on an open road. But that is not what it is at all. Light does not choose this speed. It cannot go any slower. It cannot pause, cannot drift to a halt, cannot rest for even the smallest imaginable fraction of an instant. From the moment a photon is born to the moment it is finally absorbed, it moves at exactly one speed and never any other, and the reason why turns out to be one of the most beautiful ideas in all of physics. And it comes back, as so much of this night has, to mass. Think once more about ordinary things, things that have mass. A stone, a planet, your own resting body. All of them can sit perfectly still. They can also move slowly or quickly, or at any speed in between, all the way up toward, but never quite reaching, the speed of light. Mass is the very thing that lets an object have a speed at all, that lets it sit at rest in one place and then be coaxed, with a push, into motion. And mass is also, strangely, the very thing that makes the speed of light forever out of reach for such an object. The closer you push something with mass toward that ultimate speed, the more energy it takes to push it any faster, and the harder it resists, almost as though it grows heavier and more stubborn the faster it goes. To reach the speed of light exactly, an object with any mass at all would require an infinite amount of energy, which is nature's quiet and absolute way of saying, it simply cannot be done. Mass is the anchor. It keeps a thing slower than light, always and forever, and it is also the thing that allows that thing to rest. Now take the anchor away entirely. A photon has no mass at all, and with no mass, the whole logic flips over. There is no anchor holding it back, nothing that resists being pushed all the way to the ultimate speed, and so there is nothing whatsoever to keep it slow. But here is the deeper turn of the idea, the part that is so easy to let slip past. A massless thing cannot be slow. It cannot sit still, it cannot dawdle, it cannot travel at half the speed of light, or a tenth, or any speed at all below the maximum. The very same masslessness that frees it from the anchor also forbids it, utterly, from ever resting. A photon must move at the one speed, the maximum speed, the cosmic speed limit, because for something carrying no mass, there is no other speed available to it, anywhere in the laws of nature. The instant it comes into existence, it is already moving as fast as anything in the universe is permitted to move. It was never accelerating up to that speed from a standstill. There was no standstill. It was born already at full speed. So the speed of light is not really the speed of light at all, not in the way we usually mean the phrase. It is the speed of anything massless, the natural and only pace of pure energy crossing space when nothing at all weighs it down. Light simply happens to be the most familiar thing in our lives that travels in that weightless way, and so we named the universe's ultimate speed after it. But the speed does not truly belong to light. It belongs to masslessness itself, and light merely shares in it. And this opens onto something stranger still, something it is worth approaching very softly, because it tugs gently at the edges of what we are really able to picture at all. Einstein's relativity tells us that the faster a thing moves through space, the more slowly time passes for it, as measured by those of us watching it go by. A clock racing past you at great speed ticks more slowly than the clock on your own wrist. This is not a trick of the instruments, not some illusion of measurement. It is how time itself genuinely behaves, and we have confirmed it over and over, with precise clocks flown around the world on aircraft, with the fast-moving particles that rain down through our atmosphere lasting measurably longer than they should because of their speed, even in the tiny corrections that the satellites overhead must make to keep our maps accurate. As a moving thing approaches the speed of light, this slowing of its time becomes more and more extreme, time stretching out further and further until, at the very speed of light itself, that stretching reaches its ultimate limit. We must be careful here, genuinely careful, because this is a place where the mathematics truly does break down, and an honest guide does not pretend otherwise to make the story prettier. There is no valid frame of reference that travels along with a photon. There is no proper, well-defined way to sit upon a beam of light and ask what the universe looks like or what time feels like from there. The equations refuse to give a sensible answer at that limit, returning the mathematical equivalent of a shrug, and physicists are quite right to say that, strictly speaking, there is no such thing as a photon's own point of view. So what follows is not a fact to be stated, but a careful and clearly marked step toward the edge of an idea, offered as a way of feeling its shape, rather than a claim about how things truly are. With that caution held firmly in mind, the equations seem to whisper something remarkable as we approach the limit. They suggest that for the light itself, no time passes at all, that a photon, in whatever loose sense the word can even apply, would experience the entire span of its existence in a single timeless instant. Sit with that as gently as you can, here in the quiet, holding it loosely. The light reaching your eyes tonight from a distant star may have crossed thousands of years of empty space to get here, thousands of years from where you rest. And yet the equations seem to hint that from the light's own side, if it could have a side at all, that immense journey took no time whatsoever. The leaving of the star and the touching of your eye would be, for the light, the very same moment, separated by no duration at all. The star releases the photon, and you receive it, in what is, for the light, a single seamless now. The distance is real. The years are real for us, achingly so. But the light crosses them. In some sense we can gesture toward but never truly inhabit, without aging by even the smallest fraction of a heartbeat. There is something almost tender in the thought that the most ancient light in all the sky might be, from its own vanished vantage, as fresh and as new as the instant it first left its source. We cannot fully picture it, and we should not pretend to ourselves that we can, but we can hold the shape of it, the way you hold the shape of a dream in the first moments after waking, before it fades, and we can let it be beautiful without demanding that it also be ordinary or fully understood. While we are here at the very foundations, in the country of relativity, it is worth pausing on one of the most famous moments in which these strange ideas were caught in the act and shown to be true, because it speaks directly to the light we have followed all night. Einstein's deeper theory of gravity, his general relativity, predicted that gravity is not really a force reaching across space, but a bending of space and time itself by anything that has mass, A heavy body like the sun warps the space around it, the way a heavy ball set on a stretched sheet makes a dip that other things must roll around. And light, even weightless light, must follow the curves of that warped space. So the theory made a clear and testable prediction. The light of a distant star, passing close by the edge of the sun on its way to us, should be bent very slightly as it crosses the dented space near the sun, so that the star would appear to sit in a slightly shifted position in the sky. The trouble is that you can never normally see stars near the sun, drowned as they always are in its overwhelming glare. There is only one circumstance in which the sky beside the sun goes dark enough to see them: a total eclipse. And so in 1919, an English astronomer named Arthur Eddington led an expedition to observe a total solar eclipse, photographing the stars that appeared close beside the darkened sun, and then comparing their positions to where those same stars sat in the night sky months later, with the sun far away. The stars near the sun had shifted by very nearly the amount Einstein's theory had predicted, and by about twice what the older physics of Newton would have allowed. Light had been seen to bend around a star. The news of it travelled around the world and made Einstein famous almost overnight. And it confirmed, in the most direct and visible way, that even weightless light must obey the shape of the space it travels through, bending along the curves that mass carves into the cosmos. Hold on to that, because the universe itself, it turns out, has a shape, and a changing one. And that brings us to the very last great idea to settle into tonight, the one that carries us all the way back to the beginning of everything. The light, we said, feels no time, and is born already at full speed, and bends along the curves of space. But does it change as it crosses the vast reaches of the universe? In one sense, no. Its energy is set at its birth and carried faithfully, as we have said all night. But that is true only within any single settled place. The universe itself is not standing still. Space is expanding, stretching, growing larger with every passing age. The distances between the most distant galaxies slowly opening wider and wider. And a photon travelling across that expanding space gets stretched right along with it. Its ripple, its wavelength, the distance between one crest of the wave and the next, is drawn out longer and longer as the very space it is crossing swells beneath it. And a longer wavelength means a lower frequency, and a lower frequency, through that small and patient equation, from so much earlier in the night, means lower energy. So the light slides slowly down the spectrum as it travels across the eons, from blue toward red and onward, simply because the space it is crossing keeps on growing. Astronomers call this cosmological redshift, and it is the gentle, universe-wide reddening of all ancient light. And it is important, as you rest, to understand what is and is not happening here. It is not that the photon is spending its energy along the way, burning through some fuel, the way the old discarded picture from the start of the night would have imagined. It is that the very meaning of its wavelength shifts as the stage it travels across expands beneath it. The light is not growing tired. The room is simply getting larger around it, and the wave is being drawn out by the growing of the room. And this brings us, at the very last, to the oldest light of all, the faint and ancient message that we promised, several sections and a whole journey ago, that we would return to right here at the end. So cast your mind all the way back, further back than stars, further back than galaxies, to the early universe itself. In its first hundreds of thousands of years, the whole cosmos was unimaginably hot and dense, a brilliant, seething fog of bare particles and radiation so thick and so crowded that light could not travel freely through it at all. a photon would fly the shortest possible distance and immediately scatter off a free electron, again and again, unable to cross even the smallest gap, trapped exactly as that photon was trapped deep in the heart of the sun. For a long stretch of time, the entire universe glowed, opaque, a single wall of light going nowhere at all, hot fog from horizon to horizon, with no horizon to be found. Then, roughly 380,000 years after the beginning, the universe had expanded and cooled just enough for the fog to clear. The temperature dropped low enough that the wandering electrons could at last be captured and held by the nuclei, settling down together into the first complete neutral atoms, mostly hydrogen. And with the free electrons suddenly gone, captured into atoms, there was nothing left to scatter the light. The haze lifted all across the cosmos at once, in what must have been the most profound clearing of all time. And in that moment, light was suddenly free to travel. It set out across a newly transparent universe in every direction, and it has been traveling freely and without obstruction ever since. That light still fills all of space, every cubic inch of it, in every direction you could possibly point. It is the afterglow of the universe's own beginning, the oldest light there is, released at the very moment the cosmos first became clear, when it was only a few 100,000 years old. But the universe has expanded enormously in the 13.5 billion years since that clearing, and so that ancient light has been stretched along with the growing of space, redshifted, drawn out by all that expansion from the fierce hot glow it once was, down and down across the whole spectrum, all the way into the gentle microwave band that we toured near the very start of the night. It has cooled, as the stretching cooled it, from the temperature of a glowing fire to a mere faint whisper above absolute zero, an even, patient hum at around 2.7 degrees on the absolute scale. The temperature we sometimes simply call the 3-degree background. We named it the cosmic microwave background, and it is, quite literally, the light of the beginning, grown old and soft and patient, still arriving everywhere, all the time. It took us a long while, and a great deal of care, to learn to read it. The cosmic microwave background was first stumbled upon, almost by accident, in 1964, by two radio engineers named Arno Penzias and Robert Wilson, who found a faint, even hiss in their antenna that they could not get rid of no matter what they tried, coming from every direction in the sky at once. It slowly dawned on everyone, the afterglow of the Big Bang itself. Decades later, we set out to map it deliberately and precisely. NASA's COBE satellite, in the early 1990s, measured its spectrum and confirmed that it has exactly the smooth thermal character that the theory demanded, the glow of something that was once in perfect balance with the hot early universe. Then NASA's WMAP, and later the European Space Agency's Planck satellite, mapped it with ever finer and finer precision, charting the faintest possible ripples in that ancient glow, tiny variations of warmth and coolness from place to place, only 100,000th of a degree, the seeds from which all the galaxies would one day grow. And from those exquisite maps we have learned the age of the universe, what it is made of, the curvature and the history of all of space. The whole towering edifice of modern cosmology rests, in great part, on patiently reading the most stretched, most reddened, most ancient light there is. And here, at the last, is the quiet wonder to carry with you into the closing of the night. This light is not somewhere far away, locked safely in the distant past. It is here. It is now. It is passing through you. There are something like 400 of these ancient photons in every single cubic centimeter of space. including all the space that your own resting body happens to occupy at this very moment. The light of the universe's first transparent instant is drifting through the room around you right now, faint and cold, and almost unimaginably old. The field still gently rising and falling exactly as it has since before there were any stars or any planets or any eyes at all to see it. You are bathed in it. You always have been, every moment of your life, and you always will be. It is the most patient messenger there is, set loose almost 14 billion years ago into a universe that had just that instant become clear, and it is touching you now, having lost nothing essential at all along the unthinkable way, only stretched, only softened, only grown gentle with the long, slow growing of the universe itself. The light that warms the back of your hand left the surface of the sun a little over 8 minutes ago. The light in this faint, even background left almost at the very dawn of everything there is. And both of them, the near and the unthinkably far, the new and the unimaginably old, arrive in exactly the same way, as weightless ripples in the same old ocean Faraday once felt around his magnets, each one carrying the faithful memory of where it began across all that space and all that time, asking nothing of you at all but that you happen, for a moment, to notice. That is where the journey comes at last to rest, and we will let it rest there, softly, for just a little while longer. So we come back, at the very end, to where we started, to the warmth on the back of a hand, to the soft light resting on a windowsill, to the quiet contradiction that has been touching you your whole life without ever asking to be noticed. Light has no mass, and yet it carries the energy of the sun across 93 million miles of emptiness. It inherits its color from the violence or the gentleness of its birth. It can be matter that gave up everything to become a ripple in the dark. It carries momentum enough to push a sail between the worlds, and it crosses the universe at the only speed something weightless can ever know. Born already moving, never resting, in some sense, never aging at all. And all of it, every kind, is the same thing, the same self-renewing ripple in the same invisible ocean Faraday felt, and Maxwell wrote down, rising and falling, handing its energy gently from one patch of the field to the next, all the way to you. There is no need to hold any of it now. You can let the names drift, Planck and Bohr and Einstein, the 100,000-year journey, the thin silver sail, the ancient cold hum of the universe's first morning. Let them settle wherever they like. What is worth keeping is softer than any fact. It is only this. You are, at this very moment, bathed in light that is older than the stars, drifting through the room around you, carrying the memory of where everything began, asking nothing of you at all. So rest now. The light will keep arriving faithfully, the way it always has. And we will be here again, the next time you want to drift a while among the quiet things of the cosmos. Sleep well.